Good morning, everyone. I'm Kyron. Today, I'm going to present TableFS. In this project, we're trying to enhance metadata efficiency for local file systems. This is a joint work with my advisor, Garth Gibson. The motivation behind this project is that we found even in today's big data age, there are still many more small files in the existing local file systems. The following figure shows some evidence from previous survey works, which collects the traces from the Microsoft's engineering desktop, as well as the Hadoop cluster from Yahoo. And the figure's x-axis shows a different file size, and the y-axis shows the percentage of files whose size are less than a certain threshold. And we can see for the Microsoft engineering desktop trace, the median file size is around 4 kilobytes. And even for the Hadoop cluster, which are supposed to process large amount of data, there are still about 25% to 40% files whose size are less than 4 kilobytes. Therefore, with the growing capacity of the hard disk, there will be many more files appearing in the local file systems. Rick Wheeler in 2010 challenged the Linux file system community to support 1 billion files on the hard disk. But managing metadata on small files is quite challenging, especially on the hard disk. As we know, transferring a small amount of data from the hard disk costs far less than locating the place of the data on the hard disk. Therefore, bad organization of the small data and small files on the hard disk will cause excessive random access to the hard disk. And the hard disk can only provide a limited number of random requests per second, which it cannot sustain the high throughput for the metadata-intensive workloads. However, even in today's the state-of-the-art Linux file systems, they are still not optimized for the metadata-intensive workloads. To demonstrate this problem, we have run some micro benchmark against the 3 Linux file systems, Btrfs, ext4, and XFS. And the workload we choose is to create 100 million 0-byte files in one giant directory. And the experiment starts with empty file systems. And this figure shows the experiment result. And next time is the running time, and the y-axis shows the creation throughput in a log scale. And we can see with the more creation in the directions, the throughput goes down. This is because for each create operation, the file systems need to check whether the file already exists in the directories. So the more files in one directory, the throughput it is. However, this is not the point I want to show. What I want to show is that with some optimization techniques, you can improve the throughput for this kind of metadata-intensive workloads. So the figure shows a black line, which is our prototype TableFS. We are using some techniques to improve the metadata efficiency about 10 times. So in today's talk, I will talk about what kind of optimizations we use to improve the metadata efficiency and describe its implementation. And finally, I will present some evaluation results about it. So the core design of the TableFS is trying to pack directory entries, file attributes, and the small file data in one single on-disk data structures. So the design combines 2 ideas from previous work. One is from the embedding inodes, which we are trying to co-locate the metadata and small files in one place. Therefore, we can reduce the unnecessary random reads to the hard disk. And another idea we take is trying to store all metadata into one local structure module tree. The local structure module tree is inspired by the local structure file systems, which tries to maintain the buffer in the memory and keeps most recent inserts and update keyword pairs. Therefore, it can transform random writes into larger sequential writes. Therefore, it can reduce unnecessary disk traffic. So by combining these 2 ideas, we can reduce random disk seeks. So to show how we actually incorporating these two ideas, let me first describe the schema we use to present the metadata. So in TableFS, we represent the directory and the file attributes as a key value pairs. And the key schema we choose is inode number of the parent directory, concatenate the file name. And in the value fields, we also pack the attributes such as timestamp, file size, and permissions. And also we put the file data of small files in the value field. When TableFS tries to open the file, what it does is to work the namespace tree from the root inode to the tree node it looks for, which essentially is doing multiple lookups to the metadata table. Once it finds the target entry, then it can get the file attributes and the file data at the same time. To physically store this metadata table, we choose to using the local structure merge tree to represent the metadata table. Local structure merge tree is a write-optimized on-disk indexing data structure, which are used in big table, LevelDB, and other big data systems. The main idea of the local structure merge tree is to maintain a buffer in the memory. The memory buffer will keep a sorted list of the recent inserted and updated key value pairs until the buffer grows and exceeds some threshold, for example, 2 megabytes. Then the local structure merge tree will flush the buffer into the hard disk and generate an immute sorted table file. By doing so, local structure merge tree can transform random writes and updates into large sequential writes. And on the other hand, it also maintains in-memory indexing for those generated sorted table files. Therefore, it can achieve a similar level of read performance as a traditional B tree. By incorporating those two ideas, we have built a prototype called TypeFS, and we built our prototype using the Fuse framework. Fuse framework allows us to develop this prototype in the user level process. What it does is it has a curl module daemon, which can redirect the VFS cores to the TableFS user process. And we using a layering approach, which means the TableFS uses the existing underlying local file systems as an object store. So it does not manage the raw disk directly. What it does is it puts all the metadata into a lightweight database called LevelDB, which is developed by Google, and it implements a variant of the local structure merge tree. And for the large files, the TableFS directly stores them into the underlying local file system. So after presenting the overall design of the TableFS, now I'm going to show you some benchmark results. The first benchmark result I want to show is a data-intensive benchmark. In this benchmark, I want to show even though the TableFS is designed for the metadata-intensive workloads, it does not slow down the data-intensive workloads. And secondly, most importantly, I will show you the results for the metadata-intensive workloads. Then I will repeat some of the experiments on the SSD. So we tested all of our systems on a commercial enterprise server. It has 2 cores and 16 gigabytes memory. In order to test the out-of-core performance, we deliberately limited the memory to be only 350 megabytes. Therefore, the dataset cannot be fit into memory, and is forced to written into the hard disk. And we tested our system against 2 storage devices. One is the hard disk from the Western Digital. It can provide 100 random seeks per second, and it delivers about 130 megabytes per second for sequential reads and writes. And we also test the SSD from the Intel. which can provide about 15,000 random reads per second and also 3,500 I/O per second for random writes. It also can read and write sequentially about 100 and 200 megabytes per second. We compare TableFS with the three most popular Linux file systems. One is ext4, which is the most Unix-like. It only uses a Btree to manage the directory entries. And the other two are XFS and Btrfs. Unlike the ext4, the two extensively using Btree to manage all file system metadata. And in all the experiments I show in this slide, TableFS uses the ext4 as an object store to store all its LevelDB files and other logic files. In all the experiment settings, the journaling of all the file systems are asynchronously committed to the disk using the default settings. For example, TableFS and ext4 commit the log every 5 seconds. And we make sure we are not biasing our solution. So the TableFS does at least the same amount of work as other tested file systems to guarantee the durability. So the first benchmark I want to show is a data-intensive benchmark. TableFS is not optimized for this kind of workloads, but we want to show it's still not slows down the overall performance. The workload is try to untar, grab some patterns, and gzip on the Linux source code. And the Linux source code is about 550 megabytes, consisting of 40,000 raw files. And it cannot be fit into the memory. And the figure shows the overall runtime of the three workloads. Therefore, the lower bar, the better. And the purple bar is TableFS. And we can see TableFS achieves a comparable performance as the other three file systems. From this experiment, we demonstrated that TableFS can support a variety of workloads and does not slow down the data-intensive workload. And another thing I want to mention is that the Fuse framework we use also incur additional overhead. To demonstrate the overhead incurred by Fuse, we also compare the original ext4 with an Fuse version of ext4. What Fuse version of ext4 does is we're running a simple Fuse user-level process. It simply just redirects the VFS to the user process and redirect back them again to the underlying ext4 file systems. So it just simply contains the additional context switch and the memory copies incurred by the Fuse framework. And we run the same workloads as the previous slide showed as the two systems. And we can see the dark blue bar is the Fuse version of the ext4. And it's about 10% to 30% slower than the original ext4 system. So you may wonder if we build a kernel-native TableFS, the performance of the kernel-native TableFS can be improved. Therefore, in order to estimate the kernel-native TableFS, we provide another model called TableFS Expected. What it does is it treats the TableFS code as a library and link it directly to the benchmark applications. Therefore, it can avoid the context switch and the memory copies overhead brought by the Fuse framework. And it also simulates the system calls by just write additional data to the level now. So in the rest of my slides, I will report the performance numbers for both TableFS Fuse version and the TableFS Expected version. So now I'm going to show the results for the metadata-intensive benchmark. And we taken a trace from a personal desktop. The trace contains about 1 million files and 170,000 directories. In order to just test the metadata operations, we set the file size to be only 0 bytes. And the workload contains 2 stages. And the first stage is try to create the namespace into the empty file systems according to the trace we have. And the sixth stage is to perform a variety of operations on the files randomly chosen from the namespace. We have tested 4 operations. One is the create operation, and the other is the query operation, which consists of 50% stat and 50% chmod. And we also test the rename and deletion operation. Here is the result of this benchmark. It shows the average throughput during the entire workload of the second stage. And we can see for all 4 operations, create, query, and rename and deletion, our solution is about 2 to 3 times faster than all other Linux file systems. Even with fuse overhead, TabFS fuse is still faster than the other 3 file systems. Though it's not as fast as the first benchmark, this is because in this case, we limited the machine memory to be only 350 megabytes instead of using the 16 gigabytes memory as the first experiment. So now I'm going to show you some evidence why TabFS is faster than the 3 test Linux file systems. We have collected the disk traffic during the benchmark. So the 2 figures shows the total number of disk traffic during the query phase in the previous benchmark. And the left-hand figure shows the total number of disk writes. And the right-hand figure shows the total number of disk reads. And we can see from the left-hand figure, TabFS uses many fewer disk writes than the other 3 file systems because it's using the local structure merge tree, which buffers writes and delays writes. And at the right-hand figure, we can see TabFS uses a similar number of disk read requests as other 3 file systems because it's using in-memory indexing and maintain similar performance as a traditional B tree. Therefore, combining those 2 benefits, TabFS outperforms the other 3 Linux file systems. Besides pointer queries shown in the previous metadata-intensive benchmark, we also test the range queries. We test the file system's reader operations. We're using the same traces as the previous experiment, but in this case, the file data is not 0 bytes. Instead, it has is packed with 4 kilobytes file data. And we test the 3 workloads. One is the reader or workload. What it does is simply randomly choose a directory in that traces and perform a reader operation on that directory. And the other 2 workloads are reader plus stat and reader plus read file. The difference is that for reader plus stat, for each entry returned by reader operation, the benchmark application will try to also do a stat or read file operation on that entry. And the figure shows the total runtime of the running 3 workloads. The lower bar, the better. And the purple and the light blue bar are TabFS solutions. And we can see for the reader workloads, TabFS gets a similar performance with other 3 file systems. In this case, it's not the faster. This is because the schema we choose, TabFS will read more data than the ext4 file system. But on the other 2 workloads, our solution performs much faster than the 3 Linux file systems because it packs the directory entries with the file attributes and the small file data. Actually, the TabFS is mainly designed for hard disk. However, SSD is so important today, so we also repeated some experiments on the SSD. So we rerun the query workloads as shown in the previous slide on the SSD against the 5 test systems. And the 2 figures shows the result for both hard disk and the SSD. And we can see the right-hand figure shows the throughput of the SSD case. And in this case, all the test file systems get improved by an order of magnitude. This is because SSD can provide a lot more random access than the hard disk. However, in this case, TableFS is not the faster one, but it's still a lot faster than the slower one. And we find the reason that TableFS is slower than the Btrfs because it reads more data than the Btrfs on the SSD. And we conjecture if we're using a fine-grained in-memory index to locate the exact place of the key value pairs on the SSD, we can reduce the read amplifications. However, this is left for the future work. In conclusion, today's Linux local file systems are still not optimized for metadata-intensive workloads. However, using some optimization techniques, such as pack the metadata and the file data into the same place, and using the log structure memory tree to delay the updates and the writes, we can improve the metadata efficiency a lot. And we also open source our prototype, and it can be used for the experiment purpose. This is the end of my talk. Thank you.
I am Yoshiro Oyama from UEC Tokyo. I have a question about synchronization between concurrent operations. I wonder what part of the metadata tree is locked in write or create operations. So does TableFS have a global lock, or one lock is associated with each node?
In our prototype implementation, there is a global lock for the concurrent writes.
Global lock?
Yeah.
And my another question is, does TableFS have a mechanism like transaction? So
in current implementation, we do not support transactions, but we think we can modify it to support it. But in current implementation, we do not support a transaction.
Thank you.
Nice work. I'm Kai Shen from University of Rochester. So my question is, when you have a lot of files in one directory, is there any attempt to try to group the metadata for the files in one directory near each other in your storage? So if you want to scan through a directory, it will be faster?
Yeah, the schema we choose will make the files in the same directory will close to each other, because the file entries in that directory have the common prefix. So when you store them into a local structure memory tree, it has a compaction process will make sure those entries will close to each other on the surface of the disk.
All right, all right.
Yeah.
I have a quick follow-up. That is, we play with several key value stores. LevelDB is the one we found that's very fast. So what I wonder here is, what my takeaway from this is, I think it's nice work. What I really see over here is that you have those key value stores like LevelDB that's very efficient. It does a much better job than the current file system directory management to do key value lookup. And you basically provide a mechanism so that you can use LevelDB to do the job that the current file system is doing poorly. Is that the right takeaway from your work?
Yeah, so we mainly argue we can using the local structure approach to represent the metadata, so to speed up the metadata efficiency.
All right, thank you.
Matthias Peyer, UC Berkeley. I like the idea of using a stacked approach. What I wonder is that, all the modern file systems do a whole bunch of work to ensure safety and integrity of the file system.
Yes.
And if you're using such a stacked system, you might run into a whole bunch of problems if you crash in the middle of a read, because you don't know what part of your higher level stack was already written to the lower level disk and to the lower level file system. Did you look into that? Did you look into these integrity issues?
So actually, in LevelDB there was a write head log, so it makes sure the metadata will push it to the write head log to keep the consistency of the data. And I do agree for using the stacking. There are still, because also we store large files into the underlying file systems, then there will maybe cause some consistent issue. We have implementation to make sure the data is consistent.
So on your SSD comparison, did you figure out why ext4 was so bad?
So I don't know, but we just check the disk traffic. ext4 reads a lot than other tested file systems. This is the evidence we found, but I don't know the real reason for that.
Vaishnav from Akamai Technologies. So I had a question regarding you keep the metadata and the data separate for files less than 4K, and above 4K you keep them separate, right?
Yeah. Yes.
Have you done any studies on like at what size do you want to separate the metadata and data, or this is just
yeah, we test the different file size. I think in some file size that's larger than more than 16 kilobytes, the creation workloads will become slower because we pack too many data with the directory entries. So the compression will do a lot more work. But from our the traces we found is there are lots of files that are even less than 4 kilobytes. So we choose the 4 kilobytes in our experiment.
Okay, thanks.
Hi, my name's Charlie Johnson. I work on a thing called Metabox, which front ends iBricks, and it's very, very similar except a distributed file system. And I was curious how you handled renames, because renames is an interesting problem because they happen. They're not necessarily atomic. They happen in many places.
Yeah. So actually, the LevelDB provides a batch operation that can make sure the two insertions you make will be automatically applied to the LevelDB. So we're using that to implement the renaming operations. We just insert two and batch them right into the LevelDB database.